Okay, so hopefully people were able to make at least some progress with step one, or at least understand what's happening there. So now let's move on to starting to make this a little more real, because all we've got so far is just something that checks to see if our syntax is valid Lisp syntax. It doesn't do anything with it. So the next step, what we're going to do is expression evaluation. The first steps of expression evaluation. So what we're going to be adding here is basically inside of the eval block, we're going to have two functions. We're going to have a function called evalast, and then we'll have, it's not actually a separate function, it could be, but it's not going to be the way we do it, is the apply block. So, when evalast is called, it's going to be called with that abstract syntax tree, that data structure that was read in by the read_stir function. What it will do is it'll look at the type of that abstract syntax tree. And again, if any of you are functional programmers, and I'm sorry that the dynamically typed nature of this, but we'll try and get through it anyways. Yeah, we get an object that could be several different types. And so evalast, the behavior of evalast differs depending on what that type of that abstract syntax tree object is. So if it's a symbol, what evalast will do is look up in the environment, and I'll show you how you create a really basic environment in a second. It will look up in the environment and return the value that's in that environment if there is a mapping for it. If the AST is a list, what it will do is it will iterate through each element of the list, calling back into eval, the top level eval function, for each of those elements. And then whatever the result of that is a new list that evalast returns. We're not going to actually talk about vector and hash map for this workshop. So after symbol and list, then the default case of evalast is just to return the AST unchanged. Okay. Let's see here. That's fine. All right. So for step two, I'm gonna give a demo. The examples I'm gonna do are in JavaScript this time. All right. So. You don't need to do any of that, but I'm just getting some of the code up to date for myself. All right, so what I'm going to do in JavaScript here is I'm going to copy the step one implementation that I created, and this will be the same basic process that you'll do, to step two eval.js, or whatever extension you're doing. Okay. I'm sorry? Okay. What's that? I copied it because we're basically done with step one, the step one implementation. So when you run the test, it assumes that it's going to test using the step two name for your implementation. So yeah, we could have, I could have just called it mal.js and changed the code as we went along, but I'm leaving the old copy. There's no step two in your repository.
Can we get a copy of your step one for JavaScript?
You should have a copy of step one in JavaScript.
It's on GitHub. Completed.
It's not there?
No. The tags and
So, oh, I see. You want to catch up. Is that what you mean? Okay, so if you do git checkout step one completed, again, you'll have to move your current code out of the way, but if you do git checkout step one completed, you'll have the step one, the completed step one for JavaScript, Ruby, and Python, if you run that. I'm not sure that answered your question, though.
I was just like, do we not just create a step 2 file?
Yes.
Okay.
Yeah. You don't, like, yeah, if you're just going along in one language, you don't need to do the git checkouts, and you don't need to, you're just going to copy the step 1 you were just working on and copy to step 2. Yeah, you'll be,
Require all the code that exists already in the same language.
yeah, so there's a separation between, like the reader and printer, we're not going to change anymore, and so we don't copy those. But the step, you're right. I'm sorry. You didn't actually make any modifications to step 1, but just bear with me. Most of the changes we're going to now make are in the step files.
We're going to continue to add to the same
Yeah,
file.
yeah. Yeah, the step file. Yeah, I forgot to mention that. The step 1, you're not actually modifying the step 1 the step 1 read print.js or .ruby. But in step 2, we are going to modify that file. And then after step 2, we'll copy to step 3. We'll continue modifying. And if you can run tests for the old versions of the steps, and it'll use what you had implemented for that step. So part of this is just, it's following the pattern that I used when I'm developing it. So, right. So, and the tests assume that you're going to use the same number as the test you're running. So, all right. So, yeah, if you haven't already do this, you're going to copy the step 1 file for your implementation to step 2 _ eval dot extension. Okay. So let me just, this is still the step 1 version, but it's in a step 2 file. This is a JavaScript. Basically, we have a loop down here that just reads lines of input and prints out the result of calling this read eval print function, rep function, using that string. The rep function calls read eval print in order, and those functions, read calls the reader's read stir function, print calls the printer's per stir function, and eval does nothing at the moment. But this is where, for step 2, this is really the critical point we're going to be starting to modify. All right, but the first thing we're going to need is an environment here. So what is an environment? An environment is just a hash map or a dictionary. For step 2, it'll be a little bit more complicated later, or I shouldn't say complicated. It'll have some more functionality later, but for now, for step 2, we're just going to create this dictionary. Different names and different implementations. So in Python, it's a dictionary. In JavaScript, this is an object or hash map, and in Ruby, it's a hash map. So, and what we're going to put in here is basically just some functions. And again, just to point out, I've switched from this example is no longer Ruby. This is JavaScript. And I'm going to create our basic arithmetic operations here. Oops. So again, this is just a regular hash map or dictionary. The keys are, for now, the keys are strings, and one for each of the basic arithmetic operations. And the value that we're assigning to each of those keys is basically an anonymous function that takes 2 numbers and applies that operation to it. So this is a core thing you'll need already. You'll need to implement this yourself, but I'm giving you an example in JavaScript here. One thing just as a note, in the Ruby implementation, let me just pull it up here. Oh, this has the full implementation. But here's the Ruby equivalent. The Ruby one uses symbols instead of strings for the keys. One thing I should point out, that's a bit different between the Ruby implementation is just for simplicity. I'm not using the Ruby's special Lambda function, so I just have a regular Ruby function for the read eval print function. And it takes an explicit environment here. And then later when I call it down here, I pass that REPL environment dictionary that I implemented. The other, in JavaScript and Python, we can just close over that. So you can just refer, you don't need this reference, this extra parameter here. You can just basically refer to REPL environment directly. But not in the Ruby. I mean, you could do that in Ruby too, but you'd need to use Ruby's Lambda functions. And I wanted to avoid that. So anyways, let's go back to here. So this is the JavaScript again. Okay, so when we call the, and I put this in the wrong place. If I want to use it, I mean, technically I could, but the eval function, this is the eval function parameter I'm modifying here. The eval function is going to be called with the result of reading that string into an AST. And the second argument we're going to pass to the eval function is the REPL environment that we just defined. So let me just show you the eval function. It takes these two arguments, an AST and an environment. And so the environment that we pass in when we call it is the REPL environment we just created. Okay, so I'll leave the finishing of eval for your hands-on, but I'll give just a quick, so this is not finished. Eval AST function is going to take the same arguments as eval. And the reason I split it out here from the eval function itself is because we're going to use that several times. We're going to use that over and over again in the eval function. So it's utility that I pull out. Okay, so basically you're going to have a switch statement here that tests the type of AST. And if so you're basically going to have what you do if it's a symbol, if AST is a symbol, if it's a list, and then else you just return AST. Basically that. Okay, so we're a little bit, let's see, a little bit behind on time, but if you want to go ahead and start that, start implementing the conditional, then I'll finish up the eval in a minute. Okay. So let me just go into this a little bit since we're a little bit behind. I'll start. You can keep progressing along if you want, but so if our AST instance is an instance of type symbol. Oh, and one thing I forgot, critical. For JavaScript, we need a definition of the symbol type. So we're pulling in the types module. Let me just show you that real quick. So here's the JavaScript definition of symbol. It's pretty trivial. It's just an object that stores a value, but we can identify it distinctly from other things. So if it's a symbol, we're going to do something. If and JavaScript is a little bit weird when you're trying to determine if something is an array. We'll do something there. All right. Okay. What's that? Oh, yeah. Yeah, of course. Okay. So you might be starting to see some of the structure that we went through in the crash course here. All right, so I'm going to give an implementation here. So If the AST is a symbol, what we'll do is we'll just basically, okay, so in JavaScript, it's an object with a value. So basically what we'll do is we'll look up in the environment and return the whatever's in the environment for that symbol. If it's a list, then we're going to go over all the elements in that list. And what we'll do is call eval against that. And that's it. So that's our eval AST utility function. And then we're going to use, okay, so I think I have enough here hooked together to actually show you something running. Okay, so if I just put a symbol that should be found in the environment, what happened here was, walk through this. So we read a line of input. That line happened to have just a plus in a string. Then we called, using that line, we called the read eval print function. The first thing that happens in read eval print function is read. We read that line. That line happens to have just a plus. So after the read function, we now have an object, a symbol object that contains the value plus. We take that and call eval. And we use our environment when we call eval. The environment has these certain things defined. So eval, in eval we're not doing anything except just passing on right to eval AST. We'll do a little bit more there in a second. And in eval AST, our plus symbol here matched this first case, and we looked it up in the environment. And it happens to have a mapping, down here you can see plus, has a mapping to the function, and so that's what was returned here and printed out. This is JavaScript's representation of that function, obviously. Not a Lisp representation, but that's what happened there. So if I give it a list, you can see that same function there at the beginning of the list. Again, this is weird because it's mixing two different types of printing, but I think you can see what's happening. You can see that there's a function at the beginning of the list, and then 2 and 3. 2 and 3, as I mentioned before, numbers evaluate to themselves, so nothing happened at the 2 and 3, they just passed through directly. So we gave it a list, it evaluated it, and returned us a new list. But this isn't the final functionality step 2, because in a Lisp, if you get a list, it should actually invoke that if the first position is a function. All we've done is just return it directly, and that's the change we need to make to the eval function. So what I'm going to do here is this will look a little weird at first, but I'll explain why. If the thing we got is not a list in the eval function, then what we'll do is return eval AST. If it is, so if we fall through this check, then that means we are handling a list now. What I'll do is actually, this is the weird part. I'm actually going to call eval AST and capture the result. And the reason, you know, I could have called eval AST once, capture the result, and then check the type of the original. But this gets split into more cases later, so that's why I'm doing it this way.
Well, why is this not one function?
Why is eval not one function?
Well, why don't you combine these two functions in one function?
You mean so eval and eval AST?
I don't understand the difference.
Yeah. So right now there isn't any difference. I'm about to implement the apply section. And you're right. At this point, at this step, we could have just had all the eval AST code right at the beginning of the eval. But later, inside the eval function, there's different ways that we're going to call eval AST. And so that's why I'm breaking it up right now, because it's an easy time to do it. Later there's going to be a bunch of different ways that we use eval AST in here. So that's why it's a separate utility function. It's a good question, though. Okay. So we've fallen through to this case, and we're capturing the result of running eval AST. And we know this is a list at this point because we checked to see if it's not a list, we did the first case. So it's definitely a list now. So the only thing we're going to support, though, for this step is we're going to assume that the first element of that list is a function. And then what we'll do is we'll pull that function out of that list. Yep. We'll pull the function out. We will slice off that function, so we get a new list that's just the arguments. And we'll actually call that function now using those arguments. And this, by the way, this is a little, I mean, JavaScript's way of doing apply is a little weird because you need a this value in the first position, but that's just incidental complexity. Okay, so let's see if this even does what I think it should do. Okay. So let's leave that up. Oops, whatever. Okay, so let's just walk through that real quick again. When we get to the eval function, we've already called read, so we have a data structure. If it's not a list, we just call evalast and return the result of that. So the only cases there would be if it's a symbol or if it's some number or something, or true, false, nil. Because in this case, the evalast won't call the list mode. But then down here, it is a list, so we call evalast this time and capture the result. And again, this is a little weird, but it's the structure that we will have later. So then we pull out the first element. We assume that's a function. We take that function and we call it using the rest of the elements that we evaluated.
So this could have been inlined also. On the fifth line in your thing, you could have done the application, right?
Yeah, you mean you're basically saying I could have done like eval ast like that, and then called the evalast again and got the arguments. Is that what you mean?
You state the value between, but sure. I just think it could have been inlined. I guess
I could have done that.
Like I think of eval as like one function. I don't understand yet where we're going with the function.
Yeah, I mean it is. Eval is one function, and you're right. We could have inlined some of this code. This apply section though is going to be there's going to be a bunch of cases here, and not all those cases use eval ast in the same way. So it's just eval ast is just a utility function. It's not a core part of eval. So you're right about that. It's just we're going to use it a bunch of times, and so it's helpful to have it out as a separate piece of code.
Like just as a question, is it ever valuable? So on the fifth line here, do you ast.map eval? Is it ever interesting to have the intermediate results there before you've done the application?
Have the intermediate results there before you've done the application.
Like you return you map over the AST before you apply the AST.
Yeah.
Or just the mapped over values, is that ever interesting?
The original values that you mapped over, you mean?
Yeah, the return value
Yeah.
of 1.5.
Yeah, you're kind of skipping ahead to some of the interesting special forms are where that becomes interesting. Where
Oh, okay, so like if. Okay.
yeah, if we won't run eval ast on all the values of if, because then any side effects of all the cases would be run. So yeah, but that's we'll get to that point. Okay. Let's see here. So, in fact, we're running a little bit behind, so we'll probably, I'll give you maybe a few minutes to go a little farther on this in your own hands-on. Yes? What's that? Oh, you don't have the optional. When you run the test, there's an optional setting. Yeah. all caps optional equals 0, because you're running tests for hash maps and vectors and yeah, sorry. Yeah, so let's see. We'll get this list. Probably need to. Yeah, yeah. So this is the condition. If it's not a list, then it's not. If it is a list, yes, it assumes that it is functional. For now. So in order to get regular lists, like if you want something to be valuable to a list, in step 4 there's actually a function called list. So what that'll do is basically return the arguments. There's also in step 7 quoting, which allows you to evaluate a list to itself.
So for now, then it will pending. So this step is
For now, till the next step. All right. Okay. All right. So I'm gonna move on to step 3. Oh, by the way, so the result of step 2 is basically a prefix calculator, right? I mean, that's what we basically implemented here is a prefix calculator. It doesn't do much more than that. So it'll start to get a little more interesting in step 3. And again, so I mean, we have a bunch to cover, so I apologize if you haven't actually finished your implementation at this point. Please do go back and like I said, the guide. I'll be posting this material online also. The guide has a bit slower, step-by-step, more full content basically of this workshop. So, but I want to give you the foundation so that you have at least the pieces of the knowledge and some of the terminology to really be able to make progress and finish all the steps on your own. And like I said, I'll be in the channels and answering questions and stuff. So, but let's go on to step 3. Okay, so in step 3, in step 2 we had just this single dictionary, that we use to look up our values in. But we're gonna extend that a little bit to have basically a hierarchical dictionary. And what that means is you'll have this dictionary hash map, and it'll also have a pointer to a parent. And when we do an environment lookup, if we don't find it in the current one and there's a parent, we'll go to the parent and look up, try and find the value in the parent, and so on until we get to the top of the tree. And so that's basically a Lisp lexical environment. It's just a hash map of symbols to values with pointers to a hierarchy of environments. And so, let's see here. So you don't need to do, oops. What? Oh. I'm in there. Sorry, folks. Don't peek behind the curtain. All right, so I'm gonna actually switch over to Python now. Don't run all the commands that I'm running. I'm just getting to my repository into the state for the current step. But right. So step 3, I'll copy step 2, step 3 to environment, and then your extension for your language. So again, this is Python. There's actually a new file I'm going to define. And I'm going to import a class from that env environment file. This would be the equivalent in whatever language you're working in, but I haven't created this yet. So I'm going to create this class here, and I'm going to put down the stub of this for you guys first. So I have a Python class environment. I'll have a constructor. The environment class will also have a set function. A find function, and a get function. All right, so in the constructor, we're going to take, what we're going to do is basically just create, we're encapsulating a hash map here, or a dictionary, so inside this class. So I'm going to start with an empty dictionary here, that internally, and the pointer to our parent. So that's all we have to do to initialize this, to basically be an empty environment. That's what it looks like. And so what the set function will do is basically create, in the data, create a mapping between key and value. Find, what that will do is look in my current data, see if there's a mapping. If there isn't, and we have a parent, it will go to the parent and try and find it in the parent and keep going until it doesn't find it or it does find it. And it'll return the environment, the self, or the environment that it actually found it in. And get will use find to find an environment that has it, and then actually return the mapping itself. So the difference between find and get is that find returns an environment that does have a match, and get returns the value of that match in the environment. But get can use find. Okay, so I won't implement that right away, but I am going to go over here to step 3. And so my definition of my REPL environment here is going to change, because we're no longer going to just use a regular Python dictionary. We're going to use our new hash map, or our new environment type. So our root environment doesn't have any parent environment. So then we're going to Whoops, that didn't work. All right. Yeah. All right, whoops. Okay, so there's not much difference between this and the previous, what we previously defined. We just have this encapsulating class called environments at this point. Let's see. Yeah. What time is it here? All right. I'm just going to go ahead and show you this implementation. It's not really that interesting. One other thing that set does is return that value. Just makes it more useful to have it as an actual function that returns something useful. So find if key is in our self data, return self. Else, if we have a parent, then we'll return the result of calling find in the parent. And if not, if we don't have a value for that, okay, if we don't have a value for that key, and none of our parents do, then what we'll return is just return none or nil. And then in get, we will call find to try and find that key. So what we'll get is an environment. So it might be ourself, but it might also be one of our parents that has this value. Find returns the first match up the tree. If we didn't find an environment that had the match, then technically what we need to do is raise an exception. Okay. But if we did find it, if we did find an environment with that, then we'll return the value that it has in that environment. And again, just note here that this environment here might not be ourselves, it might not be this class, it might be one of our parents that matched. Okay, so if I did that correctly, it should basically still have the same functionality as before. Of course not. Let's see here. What did I do differently? Oh. Right. So it's at this point that I really need to switch to using symbols here rather than just strings. But one thing to note here is in JavaScript, you can't use objects in the key, and so you have to do it. You'll store strings in your dictionary, but then when you look it up, you'll look it up by the string rather than the actual symbol. But for Python, we can have objects in the key position. So probably still not work, of course. Env object is not subscriptable. Oh, of course. I'm still actually trying to treat it as a regular dictionary, but now it's an encapsulated object with a method. So I won't need this anymore. Just in our evalast, our environment is now class, an object, and so we'll call its get method using that symbol. Okay, so there's no new functionality here. I think what I'll do is let's see. We have 8 minutes left, so I'll keep going on and show you the what we can do now with this is implement our first special forms. So I'll give you the stubs for this and then let you, you implement as much of this as you can. And we'll have our half-hour break before the second half of the workshop. But let me just stub this out here for you. All right, so in our apply section, we're no longer going to automatically call eval AST. So I want to actually capture the first element of the list that we got without evaluating anything. I want to capture the first the first position of the list. So I'm just pulling it out, and now I'm going to change behavior depending on what's in that first position. So if this is actually still, I didn't talk about this case, but if we happen to get here and the list is an empty list, then we just return an empty list. That's just a specific list behavior. But
shouldn't that crash? That's an error, right?
If you gave an empty list,
Like
you mean?
Clojure, you can't. I don't know what would happen in Clojure.
Actually, Clojure, yeah, that's you might think it does. In some Lisps, an empty list does give you an error. In most Lisps, though, it evaluates to itself. It's sort of a weird case. So even in Clojure, an empty list will evaluate to itself. So
The empty list means you have to code it.
what's that? I know that's what I'm saying. The empty list is a weird case. I don't think the tests at this point actually test for that, so you'll get by fine if you don't have that. I have that in there for completeness. Okay, so if the first position of my list is a def bang, we're gonna. Yep. So okay. Actually, I won't implement that just yet. The other case we're going to handle in this step is if it's a let star. We didn't talk about this in the crash course, but these are the two special forms that we're going to add in this step. So this is what changes this step, to actually have lexical environments. I'll give you a few minutes to do this, but the def bang case, what that'll do is it takes two arguments. It's a list, so it's a def bang, argument 1, argument 2. It's going to evaluate argument 2, and then it's going to take argument 1, assume it's a symbol, and bind the result that it just evaluated in the current environment. So that's what def bang is going to do. So we already have the functionality in the environment class to do that. I'll leave that for exercise just for now. Let is an interesting one. Let me just type out a example let here. Okay, just since this is probably a little unusual seeing this, I could actually format this if you like. So the let list, special form. So there's three, a let has three, so apart from the let itself, there are two arguments. The first argument is a binding list, and the second argument is the body you want to evaluate. And so what let does, let will take odd even pairs from the binding list and basically create those bindings in an environment. And the difference between let and def, by the way, is that let creates a new environment. And that new environment has a pointer to the previous environment that the let occurs in. Why don't I just... Nope. So I happen to have that step finished in the Python side. I thought, I'm supposed to be in the Python. Okay, so... Come on. Okay. So let created a new environment. It bound A to 7 and B to 8 in that new environment. and then it evaluated that last list. So it had the value of b as 8. I added 1 to it. Now, the key with the let is that once the let finishes, that new environment it created went away, and so we're back into the REPL environment. That's distinct from def, where I've now modified my current environment. Okay, so I will. We have a half-hour break now. I know there's been a lot of information we've been covering. Like I said, I didn't really expect anybody to actually finish an implementation in here, but what I do want to do is set the foundation for you to be able to go and do this. Hopefully, I mean, I apologize for the little bit of stream of consciousness here, but I hope you're following it so far. One of the things that if you are following with this and implementing everything successfully, by the end of the next half of the workshop, you'll have actually early in the next half of the workshop, we'll have basically a functioning Lisp, and by the end of the workshop, you'll have a Lisp that's powerful enough to actually self-host. And so I'll explain more what that means. But yeah, we have a 30-minute break right now. So that will take us up to 3:30. So hopefully I'll see all of you back at 3:30.